Okay,
This meeting is being recorded.
so hello everyone. Today is September 13th, 2023, and we are with Liam Eagen, one of the authors of ProtoGalaxy, which is probably the latest paper in regards folding up till this date, if I'm not mistaken. So Liam is basically going to guide us through the paper and the protocol, and basically try to resolve any kind of questions or doubts about it, aside from trying to guide us through the entire thing and help us to understand the entire concept. So thank you, Liam, very much for attending to this session, and the floor is yours.
Thanks. Yep, so I'm going to talk about ProtoGalaxy, joint work with Ariel Gabzon, like Carlos said, and yeah, I guess we'll just get right into it. So first, maybe some motivation for, why we care about folding. I mean, I think everybody here probably already knows, but we have snarks. So snark, you have an arithmetic circuit and a witness, and we want a prover to be able to convince a verifier that circuit evaluates to 1 on the witness. Lots of ways we can do this. Equivalently showing that the witness is part of an NP relation. This can be made non-interactive using fiat Shamir, but it's usually more straightforward to talk about interactive protocols between a prover and a verifier because we have this abstract way of dealing with it. There's lots of ways we know how to do this. Grot 16, Marlin, Planck, Starks, many others, variations. All have different trade-offs, some faster provers, smaller proof sizes, different assumptions, etc., trusted setup. But all of these snarks are monolithic. So we have one witness, and the prover sort of goes through, proves the witness, satisfies the circuit to the verifier, and that's it. They have the whole witness at once, construct a proof, one shot. Now, given a non-interactive snark, we can use it recursively in the following way. We can take the verifier, which, since it's non-interactive, is just another algorithm. In fact, can be represented as an arithmetic circuit. You can embed the arithmetic circuit into your circuit, and then a proof into your witness, right? So a proof for some other relation into the witness, and then by checking the outer arithmetic circuit, you verify the inner proof recursively. So recursive proofs are sort of generically sufficient to do lots of interesting things, like incrementally verifiable computation, where you have, typically you have some long-running computation and you prove it incrementally. So you prove like one step, and then in the next step, you prove that you proved the previous step and prove the next step, and so on. And then proof carrying data, which is a very sort of straightforward generalization of this, where instead of proving in sequence, you prove in a DAG. So you might have multiple incoming proofs and you check both of them and then prove the next step attached to the node in the DAG. And then more generally, recursive proofs allow us to prove things in parallel or even in a distributed context with multiple provers. And there's lots of performance or potential performance benefits that come from doing this. ZK proving is kind of inherently parallel in a way that computation is not necessarily. So yeah, and so all this is to say, recursion allows us to kind of break up snark proving in interesting ways between multiple people, between multiple units of time. Yeah. But there's a problem. Proving the verifier in circuit is often expensive. It might involve checking pairings, or in the worst case, if you don't have a sort of efficient verifier, if you have a linear time verifier, like as in the case of bullet proofs, it sort of just doesn't work at all because your circuit ends up being bigger than the initial circuit. And maybe there's ways to avoid this, but doing the entire verifier in circuit is a problem, and we would like to avoid it if possible. So how can we do that? One way is folding schemes. So rather than verifying an entire proof inside of the circuit, we define a new relation. So we have our original relation for the circuit and the witness, and then this new relation, which is in some sense relaxed, which we will expand on later. But once we have this relaxed relation, we can define protocols to fold the relation and the relaxed relation into a new relaxed relation, or fold two relaxed relations into another relaxed relation. And then if the new folded instance is valid, it should be the case that both the inputs to the folding were valid with overwhelming probability. So I mean, like at a very high level, the way this works is you kind of have your witness and you have your commitment to your witness, and you can take a linear combination of them. The details of this vary, but that's essentially the trick. And then when you do that and you evaluate your circuit over the linear combination, you don't get exactly a linear combination of the outputs of the circuit, so to speak. You end up with some error terms from nonlinearities in how the circuit is computed. So you have to compute those and send them to the verifier. And this linear combination means that we can't use or we have to use homomorphic commitments like Pedersen or KCG or something. You can't use Fry for folding, at least as it's currently used. Yeah. And so the point of doing all of this is that the folding steps, where we combine the relation and the randomized relation, are easy to check. Like I said, they're essentially taking a linear combination of commitments, and that doesn't depend on the witness size necessarily at all. You can have a very large commitment or a small commitment to a very large witness and just take linear combination. And so the folding verifier, which is the part that just checks this folding step, can be very simple, whereas the final verification, where we would check the randomized instance, can be very expensive. For example, in the bulletproof case, it might be a linear time verifier in the size of the final randomized instance, but it doesn't depend on the number of times that we've folded. Yeah, so we're able to reduce the recursion overhead as compared to kind of more straightforward recursive proof composition, because we don't have to do the whole verifier in circuit. Yeah, and so allows us to use bulletproofs potentially, although you don't have to. Yeah, so some brief history of folding schemes. They were introduced in Nova for rank 1 constraint system, and then extended to other arithmetizations like Planck and lookup arguments, and extended to folding multiple R1CS instances in Supernova for non-uniform incrementally verifiable computation, which is just like normal incrementally verifiable computation. But instead of having sort of one step that you take each time, you have potentially, a number of steps, and you take one of them and you want to be able to fold that. And then in Hypernova, we use a customizable constraint system, which is kind of like a generalization of R1CS to higher degree gates. Yeah, and then in Protostar, we kind of take a step even further back in terms of abstraction, and we just fold a polynomial. So the arithmetic circuit that I mentioned initially, in sort of typical snarks, you want to arithmetize your circuit in some way that's efficient to prove. So this would be something like R1CS or Planck or CCS. And that's because in the kind of monolithic setting, that's all you do, right? You prove it, and then you want it to be efficient to verify. I suppose you want it to be efficient to verify. In ProtoStar, in folding, right, you only do this big expensive verification at the very end. So one interesting aspect of ProtoStar is that maybe we can use polynomials that are like less efficient to find to verify in the decider at the very, very end to decide if your whole folding was done correctly. But are more efficient to fold. So, and then in ProtoGalaxy, we Ariel and I extend ProtoStar to fold multiple instances. So that's kind of what I'll talk about now. And there's some, other differences, small differences from ProtoStar. So just to compare kind of the state of the art, I think I think CycleFold is newer, but I'm not sure if it's. I feel like much of this will probably hold for that as well. Yeah. So Hypernova.
CycleFold is compatible. CycleFold is compatible with ProtoStar and actually is compatible with basically anything.
Okay. Yeah. Cool. So Hypernova folding scheme for CCS. The way this works, this is written a little bit non-standardly, but I think it's helpful to think of it kind of this way. You have your polynomial G, which in the standard way of writing it is the sum over subsets of these matrix vector products. And you're kind of applying this row-wise to the matrix vector products A1x, A2x, and so on. And you can sort of see how this is a very natural generalization of a rank 1 constraint system where G, in that case, would just have 3 inputs. It'd be like A, B, and C, and it'd be A times B minus C. And yeah, so we check that each row of this vanishes, and that's what it means to satisfy the constraint system. So the way Hypernova sort of works is it does some check in the folding verifier, so to speak, the prover and folding verifier interaction. And the way this sort of works is that you do some check to reduce each of these matrix vector products to a scalar, and then you can kind of evaluate this outer gate polynomial G on those scalars. And so in doing this, you're going to have login hash functions where n is here the number of rows in A, in A's. And the sum check will then be over degree D, where D is the degree of G. So yeah. ProtoStar, by contrast, folds arbitrary polynomials. And in particular, it is possible to fold a CCS with ProtoStar if you wanted to. This polynomial G, as written up here, is also just a polynomial in X, right? Like if you kind of imagine pulling the X out and you've got your G evaluated A times X and then A2 times X. So this polynomial can be folded using ProtoStar, just generically. And so in that case, it would be like F is equal to, or F of X is equal to this expression over all the i's. Yeah, and so when I said we take a linear combination of the witness, I mean in ProtoStar this is more or less literally what you do, right? You have your, this is kind of informal, but you have your F, you have your witness 0 and your witness 1. And if F is homogeneous, which is necessary in ProtoStar, if it's not, it's very easy to homogenize F. But just assuming that it's homogeneous, and you evaluate it over these vectors, or this linear combination of vectors, every term is going to have degree D because it's homogeneous. And so if you gather up all the terms that don't depend on X, you end up with exactly F of W0. And if you gather up all the terms with degree D in X, you'll get F of W1. And this middle part is the error terms. So folding here is basically just this. You got to compute the error terms, but you can encode your original instance satisfiability on the lowest and highest order terms. Importantly, in comparison to Hypernova, we don't do sum check. This is it. There's a randomization of the independent f equations to turn it into a scalar equation rather than a vector equation, but we don't do sum check. So that's probably the biggest difference, I think, besides the generality to Hypernova. And because protostar is so general and f is just a function or a polynomial, it's very easy to support lookups and non-uniform incrementally verifiable computation efficiently, just by sort of constructing your f in an appropriate way. And this is an interesting part of the paper where there's these constants that sort of appear in analyzing how the prover performance, or what the prover performance is. And it's hard to say generically because the f is so general that it sort of depends very much on what your f is, right? Like in the worst case, your f could be very expensive to compute, but that's typically not the case. So anyway, and I think at this point, it's still kind of an interesting open question, how much benefit this unstructured f gets you compared to something like CCS, which is more structured or Plunkish or whatever. And the trade-off ends up being in the decider. So if you're doing a lot of folding, you'd kind of expect that maybe there's some benefit from having a highly unstructured f, but you pay for it in the decider. And, you know, I guess we'll have to see. So protostar supports binary folding, right? We have an instance, and a randomized instance into a randomized instance, or two randomized instances into a randomized instance. And that's sufficient to fold. Here, it's just like n instances and m randomized instances. You just sort of fold pairs of them n plus m times. You can fold in a line if they're produced as part of like a IVC thing, or you can fold in a tree if you get all of them at once, which is maybe better for definitely better for parallelization. But yeah, ProtoGalaxy instead supports folding sort of all of the instances at the same time. So when you fold in pairs, you have a hash for each pair that you fold, and you do a scalar multiplication for each pair that you fold. When you fold multiple instances at the same time, we're able to avoid some of that overhead, which is the goal of protostar. So for example, we have a k MSM instead of k kind of independent scalar multiplies, which for large K is potentially significant savings, especially because you're doing all of this in circuit. So computing k MSM is cheaper than computing k scalar multiplies separately. And yeah, there's some other differences. I don't know. I suppose, yeah, the main ones are that we use, instead of protostar, which has this thing here, we have Lagrange polynomials here, which, you know, more straightforwardly generalizes to more witnesses. And the randomization of the f's uses a different constraint separation, but that'll probably make more sense in a second. This is taken from the paper, and it's the verifier, the folding verifier complexity for the different protocols. So we have Hypernova for, I think, just two inputs here. Protostar, ProtoGalaxy, and so there's actually two types of ProtoGalaxy. There's, well, I'll talk about it in a minute, but one of them uses a multivariate sum check, and one of them uses a univariate kind of zero check mod z. And the basic difference is the number of hash functions. So you'll notice here that this k comes out because, oh, and then the sum check version also folds multiple accumulators. But yeah, you know, anyway, another difference between protostar and protogalaxy is that protostar has a sort of constant size accumulator, and as a result of that, they have these two additional group operations that you have to do in circuit. ProtoGalaxy uses just log n scalars. And so the size of the accumulator is not constant, but you don't have to do the group operations in circuit, the group scalar multiplications, I should say. Yep, so just some definitions. F is a prime field, CM is a commitment scheme. CM here, like I think there's a footnote about it, but it's not necessarily like one commitment. It could be more commitments, but for the analysis, like for example here, I think we assume that it's one commitment everywhere. But Protostar, in addition to being a folding scheme, is a kind of a compiler for special sound protocols into folding schemes. And in that case, you have multiple commitments corresponding to different rounds in the special sound protocol. ZVEX, vanishing polynomial, typically like a, k to the x minus 1 because of FFTs, but it doesn't have to be. The Li are Lagrange polynomials, so these are going to be 1 when evaluated on Ri and 0 when evaluated on the other roots of Z, standard. K will be a Boolean hypercube, which it's just bit strings of dimension log K. EQ is kind of like it's sort of like the multivariate, analogy to Lagrange polynomials. You kind of like write it like this, right? Like the B encodes the index into the Boolean hypercube, and the I is the index into the roots of Z. But you can see here that if A and B differ, and they're both bit strings, then, or I should say, if they're both the same, then either every value is, or each value is 1, in which case this term will be 1 and this will be 0, or they're both 0, in which case this will be 0 and then this will be 1. And if they differ, then both of these will be 0, so the whole product will be 0. So EQ is only 1 when A equals B over bit strings. The MLE, multilinear extension of a vector, is just this multivariate, multilinear, I should say, polynomial that when evaluated at the bit string B gives the V with index B. And here I'm kind of abusing notation, but if we're indexing V with integers, then this would be the integer with those bits. And then finally, POW is just a function that we use for taking random linear combination of constraints. And it's just the product of the xj's. And so, it has this nice kind of thing where if you evaluate it on these powers of 2 to the I, powers by 2 to the I, you get x to the I. So Protostar style folding. So we're going to fix some polynomial f of degree d that takes some witness omega of length m and produces some vector of length n, and we say that the witness satisfies this function, this polynomial, if it's 0 on omega, and it is an element of the relation if phi is a commitment to omega. So we have our relation, and this is super general, right? F could be R1CS, CCS, some weird polynomial that is useful in some situation. It could have lookups and non-uniform stuff and so on. And then in order to define the relaxed version of this, we can add E and beta to the instance. So we're going to have phi, which is the same commitment, beta and E, and then omega. And this is an element of the randomized relation if the linear combination of f of I of omega by pow I beta gives E. So the intuition here, I guess, is that eventually we're going to have like omega naught plus x times omega 1, or omega naught times Lagrange plus omega 1 times Lagrange. And when you do that, you kind of end up with some error terms. And as long as the folding verifier checks that the error terms are constructed correctly, then everything works out. But you have to keep track of that here in the randomized relation.
Can I ask a question
Mhm.
here? So this is sort of similar to what is done in Protostar, but with like two challenges that they use for the final for the like gate compression trick. But here you're adding logarithmic amount of challenge, and this beta is a vector actually, right?
Right.
And are they actually challenges, or are they like just some additional variables? How does it work here?
So this is a good question. The betas are they're a little bit like challenges. They're sort of like a folded object that includes challenges. I think it'll be explicit on the next slide, but in Protostar, instead of using so these POW functions have log degree, log the number of log n, right? And they're log betas. And like on the previous slide, they're just this product thing, which has log terms because there's log bits in I. In Protostar instead, they have two vectors of length square root n, and each sort of random coefficient here is just a product of one of those two. And it's sort of an interesting space of possibilities here because you have this POW I, right? And here we're taking log inputs. But you could imagine instead that POW I was like in base 3 or something, right? And so instead of having x squared, x cubed, x to the 8th, it would accept like 2 times log 3 values. And be like x squared, and then like x to the 3rd, and then x to the 6th, and yeah, maybe this is not a good thing to explain in words, but it's sort of the tensor decomposition of like a vector of powers. You can sort of factor this tensor or this vector into a tensor product. And so Protostar does the other extreme. It factors it into just two vectors of length square root n, whereas we here factor it into log n vectors of length 2, or implicitly. Yeah, so to answer, I think, your question, beta is kind of like challenges, and it includes challenges, but in order to fold, it's not like just a challenge, right? It's not just powers of something. It'll be powers of something plus, random linear combinations of other stuff.
Yeah, okay. So specifically, but your relaxed relation is just this equation. It has no addition. In Protostar, there will be additional equations on powers of challenge.
Oh, definitely, yes. There are no additional equations.
But here it is just one equation.
That's right, yes.
Okay.
Yeah, cool. Yeah, this is different. And just, some people have asked me about this sort of this transformation, because the way the paper is written, we fold one R and one randomized R. But if you wanted to say fold two R's, there's this very like straightforward way to lift from R to the randomized version, because if you take, in this case, this should be a vector of betas, but if you take any like random vector of log betas, then your E is just going to be 0. So yeah.
Sorry,
Okay.
one question. What if you want to fold two R rands together? You are forced to relax one of them at some point, or because in Hypernova, for instance, when you execute the sum check, it's not only to kind of like reduce the problem into a smaller one, but you are also basically applying some re-randomization of the terms. So the randomnesses are homogeneous, and then you can fold things together. What happens here?
So I mentioned before, there's the two ProtoGalaxy style foldings, but I think essentially the same thing will happen. If you have two R rands, then we need to make the betas the same for both of them to fold. And that is what we do. When you fold multiple so if you fold two R rands, you end up with some linear terms in here, and that turns out to be fine. We can still do everything in linear time. If you have like many betas in there, then it ends up being a bit of a problem, and that's why we do the sum check ProtoGalaxy as well, which I'll talk about like second. But
Okay.
yeah, I think to answer your question, yes, you have to make the betas the same and then fold like in Hypernova, I think.
Yeah, thank you.
Then Protostar, you do not need to do it. In Protostar, you just fold stuff with different challenges, no problem. You just treat it as a single equation of degree. In Protostar d plus 2, here it will be d plus log n. And fold.
Yeah, yeah. Well, like you're saying, like the betas are part of the, I guess, the witness or the instance, and then
yeah, they're like public inputs, basically.
Yeah. Yeah, I guess maybe my answer to the previous question was not quite right. That I guess that's actually more like what you do in ProtoGalaxy. Yeah, okay. In the sum check folding multiple accumulators thing, it's more like the protostar thing where you treat the betas as part of the instance and you fold all of it and you just treat them as like any other variable. And yeah. Yeah, okay. Yeah. Okay, so 2 vanishing checks, technique 1, mod Z, we're just trying to show that v is 0. Yeah, so px is like this. Maybe we compute px in some way that is not just going to result in identically 0 over here. And then if p is 0 mod z, then v is 0 mod z. Yeah, and so if you want to test this, it's very easy. Pick a random value, evaluate it at x being the random value. So in here, right, we're gonna have something like this, some linear combination of Lagranges, and it will appear inside of f here. And when we do that, f is of degree d, and this is of degree k. So when we compose them, the degree will be d times k. So the degree increases linearly in the number of instances to fold. And there's also this extra log d that comes from working with higher degree polynomials, just multiplying them and so on. But it's simpler to describe, and it uses fewer challenges. So that's why we included it in the paper. The randomized sum check is the other kind of vanishing check. So we still have a vector v. We want to show that it's 0. Pick a random r, maybe a random powers, or a tensor product of some random values, or just and then summing gives 0 if v is 0 with overwhelming probability. Just like
could you stop a bit on technique 1? Like, could you like wait a bit with technique 1?
Oh yeah, sure.
I do not understand it. So you're trying to fold to just fold or multi-fold right now?
Just fold. Well,
just
yeah,
fold 2 instances.
No, this is for k instances. Each L is going to be the Lagrange for x to the k minus 1. So the idea here is that p is going to be of degree k. Roughly. As written, it's kind of abstract and maybe a little hard to follow without the concrete.
Okay, I'm just trying to compare because like I was implementing protostar folding for arbitrary polynomials, and there is of course an FFT of the grid D, just because you need to compute your cross terms. But here you're saying that if you're doing it at Lagrangian basis, you can fold multiple solutions.
Yeah, you can fold multiple instances with these Lagranges, and so like I guess I just skip ahead maybe. Yeah, it shows up here, right? So we have our instances. This is what we're doing, right? We're folding one randomized instance and a bunch of pure instances, and inside of F we have the randomized one and all of these, and so this whole thing will be of degree k, right? and then f is of degree d. And so that's kind of how it shows up. And
Oh, okay, I
then,
understood. Okay. It seems it's clear for me, but yeah,
okay.
okay, maybe. Mhm.
Okay. Yeah. So degree k composed with f is going to be degree k times d. Yeah. So here we take the random linear combination, and if we use multivariate sum check, it'll have log. It should be log k challenges. Or no, it should be log n. Well, it depends on the length of v. It's not specified here what the length of v is. And it turns out that this is what we will use to fold multiple accumulators.
One question here.
Oh,
Sorry, go on, Lev, go on.
Yeah, my question was that this sum check will be against a polynomial which is not multilinear but of multi-degree d, because the result of application of your f to the linear polynomial, multilinear polynomial, right?
That's right, yes.
Okay.
Yeah.
So I have another question, which is in this technique too, if we applied something like zero-morph, for example, and we go from the multivariate to the univariate world, do we end up in similar results as in technique one? Not in the sense of the Lagrange, but in the sense of performance, amount of operations, and asymptotics, or
No,
do we have another landscape?
I think the right way to think about using zero-morph to go from multivariate to univariate would be kind of like at the end, so to speak, right? Like the degree dk that you get in this univariate case is eliminated by using like multivariate sum check here. Then after you use multivariate sum check here, you would use something like zero-morph. I mean, in this case, I don't think zero-morph would actually quite make sense, just because you're not really evaluating like an MLE. You're taking a linear combination of things in a sum checky kind of way, but you already have them as separate commitments. But no, I would say like the way you have like this expression, and you can either like sum check it, and then you reduce it to MLE evaluation claims, and then that's where you would use zero-morph, or you evaluate it on a univariate, in which case you have a quotient computation and a higher degree, but you use fewer hashes. And this is like, I mean, this is like a pattern I think that shows up all the time. It's kind of a lot of the recent work, I think, has been taking stuff that was written using like KZG and quotient computation, and seeing if you can shift it to just use sum checks. And I mean, of course you can, and then seeing how the trade-offs play out. That's the main difference between these two. I think zero-morph just wouldn't really affect that.
Okay, thank you.
Oh, and I think I have another question about this randomized sum check version. So if you are doing IVC, then it's not exactly clear for me. So, for example, in sum check, you need to open some multilinear commitment in the end, ideally, right? So in Hypernova, you like carefully defer this to the later rounds of IVC. So you only need to do the opening once in the end. But here it seems you would need to open it right now, right? Like after the folding.
So it's a little bit like sorry. So the difference is basically in the randomized sum check version, we're not, so in Hypernova, right, you have your x, and you have you have a times x, and then you have these MLEs that you evaluate, and then you're saying you fold the evaluations. Here you have like multiple instances, and you use sum check to take a linear combination of the instances. You at least as protostar is written, you don't fold that. You actually, in the folding verifier, you just take the linear combination of the instances. If that makes sense. You don't take like an MLE and evaluate it. You kind of have multiple instances, and then the step where you would ordinarily have an MLE evaluation, you just take a linear combination of commitments in the same sort of structured way.
But you would need to open them in different points eventually. So you cannot naively take random combination.
I can jump ahead.
Okay, maybe we get to. I hope we get to.
Yeah, sorry. Yeah. Yeah, okay, here. Okay, yeah. Yeah, I hope it'll be clear when we talk about it more concretely. Okay, so this is the mod z vanishing check. And so it's just going to be some algebra, but we start with a randomized instance, and we have beta, and then we have a bunch of instances here that we want to fold into a new randomized instance with the stars. So the first high-level step is we will refresh the beta with new randomness in light of these new instances that we're folding. We'll kind of like lift all of these instances to use the new randomness, beta prime, it should be beta star, but then combine all of these new lifted instances with the same randomness using the Lagrange zero check, which is analogous, I think, in some ways to the hypernova, lifting or folding of evaluations. Choose a random value to evaluate the Lagranges, and finally, just compute this new instance after we evaluate the Lagranges. So the way this works is pick a random delta, linearly interpolate between the existing beta and the new delta, and this is how we're going to generate the new randomness beta star or beta prime. This polynomial f is going to be this, and you'll see that when x is 0, this just becomes pow I of it should be beta. It's written backwards. It should be pow I beta. So beta plus x delta, and then that would give you e, and these error terms.
Here, if we have beta prime coming from another random instance, how this beta prime will be included into this f of x equation?
Yeah, this version of ProtoGalaxy does not support folding multiple.
Okay. Fair enough.
Yeah, it's a good question. I mean, the one way you could do it, at least in principle, is here, instead of having beta plus x delta, which is what this should be, you'd have like beta 1 times a Lagrange plus beta 2 times a Lagrange, and so on. When you have k accumulators, right, this inner expression would be like degree k, and then this outer pow thing is degree log n. So the degree of this whole factor is going to be k times log n, and you're going to need to do a lot of polynomial multiplications of things of degree k, and that is specifically what we want to avoid with the sum check version, which it does. It avoids those log or those degree k polynomial multiplications that would come from there.
That makes complete sense. Thank you very much.
Yeah, so we send these error terms, we receive this alpha, and we would compute the new beta here.
What is a in the third?
Yeah, I just noticed that I think that might just be a typo. I'm sorry. This thing.
Yes.
Yeah, I don't think that's supposed to be there. It's supposed to just be sum of fi xi here. This part. Yeah. And I guess maybe one important point that we should dwell on a little bit. I haven't written it down in the slides because I felt like it might be a little bit too dense to fit into the slides, but I can look at the paper if anybody's interested. Anyway, you can construct this f. So this f has degree log n, right? Because this is degree 1, and this is degree log n, and so degree log n. And if you were to compute it sort of naively, you could compute each POW using, I guess it's something like log, we'll call it like, O of log n. I think it's like O of log n squared or something like that. Field operations, right? Because it's a product of these linear terms, and there's log n of them, and so on. It's like log n times log n squared, maybe. And then you'd sum them all up. So that would be an additional like factor of n. Or you do that n times, I should say, and then you have to sum them all up. So the naive way of computing f would not be O of n in the number of f's. What we do instead in ProtoGalaxy and is you start out with a tree, and at the leaves of the tree you have all of these fi omega values, which we assume that we already have, which is reasonable, I think. Then if you think about how these POWs are structured, they're products of log terms. And as you go through the bits of I, each term appears or does not appear based on whether or not I is 1 or 0. Because remember, POW is, when it's evaluated over powers, it actually just gives you the power. And so in our tree, we have all the f's at the leaves. And then in the first level, you have like the first bit. And so like, maybe it's the highest order bit, I'm not sure. But like these two values differ in only 1 bit, right? The first term and the second term. So you have 0 and then like 1. And then the factors label the edges. And so we start with f0 here, and we start with f1 here. Then we would take the first factor of POW, multiply it by f0, and then multiply the, I guess it would actually be 1, but we'd multiply it by f1, and then add the results. And so we do that for each pair of leaves. And so there's n over 2 pairs of leaves. And then the second layer of the tree is labeled by linear polynomials. We can do the same thing again because of the structure of POWs. So in the second layer of the tree, we would multiply this one by a linear factor, which we can do in time linear in the degree of the node. And this would be multiplied by 1. Then we add them up, and we get a degree 2 term on all of the second level, then a degree 3 term, and so on. And so the total amount of computation that you have to do here is going to be like n over 2 times 1 plus n over 4 times 3 or 2, and then n over 8 times 4. Anyway, the degree increases linearly as you go up the tree to log n, and the number of leaves or internal nodes at each level decreases exponentially. And if you sum up all of that, and that's how much field computation you have to do, it turns out that f actually only takes O of n field ops asymptotically to compute, even though the degree is log n here, and the sum has n terms. So this is actually, I think, fairly similar to how like linear time provers for a lot of multilinear stuff work. But in this case, we're working with polynomials, so there's the additional complexity of the degree. And yeah, this allows us to have these log n beta values in the instance, and still have an O of n prover.
Sorry, and another quick question. So do I understand correctly that all the cross terms that you send are field elements, but you actually still need the commitment to omega? I mean, in the instance structure, you still have the commitment to the witness.
Definitely, yeah. Phi is the commitment to omega. That's what you're asking?
Yeah.
Okay, yeah, cool. I might try and go a little faster. Sorry. Yeah, so we want to linearly combine. So now we've computed this new beta, and we can just lift these to use the new randomness. So since CM is linear, well, what we want to end up doing is take a linear combination of omega and these omega i's, and then since the commitment is linear, we can similarly take a linear combination of the phi and the phi I. Yeah, and so there's this helpful little lemma in the paper. It's I think not super surprising. There's a very simple kind of argument for why, but basically, if we evaluate f on this sum of Lagranges, then the f kind of like commutes in. So we end up with f of omega times the first one, f of omega I times the rest of them, and then this quotient term over here. And to see why, if you evaluate both sides at a root, rj, right, all of these terms except for one will go to 0, and then lj will go to 1. So we'll have, when you evaluate this at rj, f of omega j, and similarly, when you evaluate this at rj, all of them will go to 0 except for 1, and you'll have f of omega j. And then you'll have this just goes to 0 because zrj is 0. So both sides agree on all of the roots, and that's basically all the information we need. All of the other stuff is encapsulated in this error quotient term. So the prover computes Q, which does require the sort of degree D FFTs, I think, that we mentioned earlier, because F is of degree D, and at least degree D, right? And so, yeah, we compute Q and just send Q.
Do you get, so from this lemma that you have here, do you get any benefits from being able to remove the omegas from the, like, from being together with the Lagrange polynomials? Like, can you basically pre-compute something thanks to have this lemma equality holding or not?
I don't know. I think probably not, but I'm not sure.
So how's f of omega not pre-computable? Maybe I'm missing something then.
Oh,
But
f of omega is
yeah,
definitely pre-computable. Yes,
and so
that
happens with f of omega y, right?
yeah. In fact, all of these, because the omega i's are just part of the relation, will go to 0. So like this
Exactly.
is just 0. Yeah, and then this comes from here, which you might assume that we already have pre-computed, and
Okay,
so
fair enough. Okay.
in fact, all of this just vanishes, and we're just left with this, which is
Yeah.
what we're gonna, yeah. So after we send Q, the verifier chooses gamma to evaluate, and yeah, we're just gonna sort of plug that in everywhere. So if you look here, f of omega, actually, I guess a little confusing, but yeah, whatever. Yeah, we end up with the E that comes from the L0 at omega evaluated here. We end up with the linear combination of commitments that we mentioned from here and here, and we end up with the linear combination of witnesses from here and here. And that's it. Now phi star, beta star, E star, and omega star is a new randomized instance. And if, I mean, if you sort of go through the paper, I think it's not too hard to see how this you can write an extractor, to show that if this is a valid random instance, then this must have been a valid random instance, and these must have been valid instances. So yeah, that's the first version of ProtoGalaxy. Yeah, so the second one. Here, there's, in the paper, we talk about folding multiple accumulators or folding, accumulators and instances, but I think it's probably fine to just look at the folding multiple accumulators case here, because like I said before, you can sort of trivially lift instances to accumulators maybe you don't want to, maybe it's more efficient to not do that, but the paper has more details. So in this case, like we were mentioning before, we have all these betas that are different for each randomized instance, and we want to kind of make all the betas be the same or something like that. And if we were to try and fold like protostar or try to make the betas the same in some other way, you end up with this issue when you use the Lagrange polynomials because they're of degree k and the POW function is the degree log n. So you'd end up with like a k log n here and a kd from the k in the inside of the f. Yeah. So this is exactly what I mentioned before. We have these degree k polynomial multiplications that we'd like to avoid. And the way we're going to do that is to use the randomized sum check. Yeah. So we have k is a Boolean hypercube.
I'm sorry. Can you like wait a bit? So,
yeah, sure.
So it is possible. It is possible to add multiple accumulators in this version, right?
With the Lagranges, like
yes.
these? I mean, it's definitely possible.
I mean, in protostar, for example, it's okay to consider gates of relatively high degree, like d equal to, I don't know, 50 or something like this. And
yeah,
log n is clearly smaller.
I'm sorry?
Log n is clearly smaller than d that you can afford in protostar, for example.
Okay, sure. That's true.
I mean, I'm not understanding the third bullet point here. So you're saying that I will be much harder to compute, or what?
Yeah. That is what it's saying. So the tree computation I was describing before, where you have the leaves and then you have the factors that come from the POW along the edges, and then you kind of compute everything in linear time. When the degrees are of degree k, labeling the edges, it's no longer linear, or I should say, I mean, it's linear in n, but it depends then on k.
Okay.
Yeah, I guess it's a matter. Yeah, no, it definitely is possible to use the Lagranges in more or less the same kind of way as here, right? Instead, we have the Lagranges with the witnesses. You could just as well have the Lagranges with the betas in here, and the Lagranges with the witnesses in here, and all you'd end up with is just a polynomial of higher degree, and the POWs would be more expensive to compute. But that's, I mean, not necessarily like a problem if, yeah, depending on the, I don't know. Does that answer your question?
Sort of. Also, okay, I'm sorry that I'm like stalling the lecture, but I really want to understand some parts, and they're not currently clear. So when you were folding, can you maybe open the previous slide? So when you're folding, so this Q is also I mean, I have an impression that at some point you need to send some commitment, maybe to the quotient polynomial or something like this. But you are saying that you are only sending field elements.
Yeah. So you have to send, I suppose you have to send like an oracle to Q. You don't have to, you can send the field elements of Q. That's fine. You can send a polynomial commitment to Q. It's, I think in the paper we just send Q.
Okay. Okay, well, whatever. It's relatively low degree, sure.
Yeah. Maybe that's another reason why you'd prefer to avoid adding more here, because when k is very big, sending q is large, right? It grows linearly in k, because Q comes from this like composition of degree D with degree K, or degree D plus log n with K, in which case it would be even bigger. And then you'd have to send a commitment to Q, but maybe that's fine. It would definitely work, I think. Okay. All right. So this is the sum check version. Right, we have the randomized instances. We have a Boolean hypercube of dimension log k. We're going to sample some randomness as before. And here we will define this multivariate, which, yeah, I think this multivariate, if you like ignore this term and you kind of squint and pretend these EQs are Lagranges, is sort of what we were just talking about, right? You'd have like your Lagrange of x here times beta, and you'd have your Lagrange of x here times omega, and yeah, and then it would be a univariate instead of a multivariate. You'd replace b with a capital X. But here we have this multivariate, and because we're doing a sum check, vanishing check, we need these sort of randomizers out here. Yeah, and if we think about this multivariate and you evaluate it at each j and k, then this sum, everything will go to 0 except for one of the EQs. Similarly here, all of it will go to 0 except for the EQ where L equals J. So we're going to end up with beta J and omega J in here. And then this is just going to be J times delta. And so given our randomized instances, it should be the case that the sum of pow beta J and omega J here gives EJ. That's from the definition of the randomized instance. And so it should be the case that G evaluated at each J in the Boolean hypercube gives this value. So if we sum over all the values in the Boolean hypercube, you get G of J minus this value should vanish. This is what we would like to check. If this is the case, then it should be also the case that each of these is a valid random instance.
One question here. So here we just have a randomized instance, but we don't have like the regular ones. You have said that basically you can lift the regular ones into being randomized ones and then plug them in. The question is, do you get any savings? Like, is there any way, I guess, is the first question, to merge together randomized and with non-randomized, so like all at the same time, a la hypernova, which is exactly what happens in hypernova. Well, yeah, it's exactly what happens. Yeah, exactly.
Yes, it is. In the paper, the section before we describe folding multiple accumulators, there's also the folding instances with an accumulator sort of in the previous way. But if you want to do n randomized instances with m non-randomized regular instances, yes, what you'd sort of do is you do this to combine the randomized instances and to generate a new beta. And then you would use that beta with the non-randomized instances and then fold those.
Okay.
Can't we just like in this setting, can't we just lift every non-randomized instance to a randomized one and then use this thing as a black box?
Yeah, you can. I think it might be slightly more efficient to do it the other way, but I mean, it's not obvious to me saying it right now if that's actually true. But yes, you can definitely just lift it. So in that case, you just like pick another random beta, say, for all of the non-randomized instances, and then you end up with randomized instances, and you get a 0 in here, and you just do this. That would work as well.
Is it the case maybe that you could go the univariate / Lagrange way for all of the non-random ones? fold them and leave them all together into a random one and then go for this?
Yeah, I think that would also work for sure.
Will that bring you any benefits? I don't think so, right? It will basically be the same.
Yeah, I don't know that it would have significant benefits. Like we were sort of talking about, when k is large, the Lagrange version, I think, starts to make less sense because of how big q ends up being.
Which is theoretically weird, no? Because normally you use Lagrange when you have big things. So it's a bit counterintuitive, no? Like, I mean,
yeah, it's not like so big that it's impossible to work with. It's just like, I think less efficient probably than the sum check version.
okay.
Although I don't know. I guess it's sort of an empirical question how the trade-off ends up working out. But hashing, I think, in circuit is fairly cheap. So
Yeah,
I don't know.
fair enough.
Yeah. Okay. So this is the sum that we use sum check on. So we're summing over these j's, and in each round, we're going to make one of the bits of j a variable, send a degree d plus log n, right? Because this is log n and this is degree d. And then each of them will be evaluated on a linear polynomial. Yeah, and so we'll send that, and then the verifier will choose a random gamma, evaluate that, move on to the next j. And it turns out, I think, that basically, I think it's very similar to the tree computation I described before. In this case, the leaves end up being these degree d f's, and the edges are once again labeled by these linear polynomials that come from inside of here. And so we can still compute kind of in a way that is linear in n, linear in the number of f's. We can compute each of those responses in the sum check protocol. In the paper, these are called PA polynomials, I think. Yeah, and so that's pretty convenient. We like to have linear things, and ultimately it reduces to this evaluation claim for G. And a while back, I was saying how we don't like have an MLE of the witness. We just have this. This is the MLE that we have to evaluate, this G of gamma. And evaluating G of gamma does not require like simplifying beta or simplifying omega. If we plug in gamma here, this just becomes a scalar. And then this is like a linear combination of the betas by EQ gamma, or yeah, EQ gamma L times beta. And this is a linear combination of the omegas by EQ gamma L. And so on the next slide, I guess it'll explain, but after running the sum check, we want to check that G of gamma equals some constant C that's produced by the sum check. And so in order to do so this check ends up becoming the basis for the next randomized instance. So we have G of gamma is going to equal this expression evaluated at gamma equals C. So to put this in the right form for a randomized instance, we have to divide off this extra EQ evaluated at gamma, which is what we get here. And we have to combine this sum evaluated at gamma to get the new beta, which is what we do here. And similarly, we have to combine the omegas by the gammas. And then since we've combined these omegas by these EQ with the gammas, we combine the phis with the EQs with the gammas. Yeah, and so this is the part where you're evaluating at gamma. This computation. And this computation specifically is evaluated in the folding verifier. The folding verifier checks that these commitments are properly linearly combined. And so yeah, this is just an MSM of size k.
So the second equation is analog of computing your Lagrange combination of Lagrange polynomials at random point. Basically.
Exactly. Yeah. It works out almost exactly the same. You have the Li gamma as sort of like
Yeah.
the EQ gamma. Yeah.
Like, how is it an MSM of size n? Like,
I should say size k, I think, because this is a size k.
Isn't it too big though to put it inside of the circuit?
No, you're folding k things. Of course, you need to linearly combine them.
Oh, yeah. Okay, fair enough. I forgot about the multifolding. Okay, yeah. If it's multifolding, yeah, that definitely makes sense. Okay, yeah.
Yeah.
This is
Yeah.
like extremely similar to Hypernova's last step of the multifolding. Like,
yeah.
it looks the same, but changing. It's just changing the names, though. Yeah.
Yeah. Okay. Yeah, and then just some stuff about the verifier. It has to check this KMSM we were just talking about. So compared to Protostar, you'd have k scalar mults in each of the pairwise foldings. And because of Pippinger, this can be faster to prove. There is some interesting work, I guess. It's not like in the paper, but I think it's interesting to explore. I thought I would include it in the presentation. I mean, I can talk about it if I don't have like concrete stuff, but essentially here we're checking a linear combination of commitments, right? We have the phi j's and we're taking a linear combination by these EQs. The folding verifier doesn't necessarily have to compute that. Maybe it's possible for the folding verifier to simply check that phi star is this linear combination. And it's possible using inner pairing products to check this linear combination.
I think I have a comment on this. So at least for me, it seems that when you are in the high degree world, then your inner product argument is likely less efficient than properly done Pippinger because it's actually quite a low degree. Your witness, I mean, if we are talking about your inner product argument, then its witness, it's actually of degree 2. Its circuit is actually very wide circuit of degree 2. Because, and some of actually of degree 1, because you are computing your witness in a bunch of points. And so it's a bit hard to come up with to use to our advantage that we have access to the polynomials of high degree. But maybe it's possible to come up with some trick.
Okay, I'm not sure I completely follow.
We could discuss.
Okay, sure. Yeah, and that's all I have. So any further questions or discussion? But yeah, that's it.
I have one question, which is in regards of deciders, which we haven't spoken about, and I'm not sure in the paper like was deeply explored. And what I wonder is from like, since the check is really similar to Hypernova, what I presume is like mostly what works for it should also work for that protocol. But do you know, do you have any kind of preferences, or do you think that something might be better to use in the decider, like some kind of protocol than any other one? Like, for instance, is it better to go for Spartan, or is it better to go for Groth or Plonk? I don't know, whatever it is.
Yeah. So I think that it's not necessarily possible to say in general, it depends very much on your F. If your F is chosen to have, structure that aligns nicely with a proof system, then it probably makes sense to use, the snark that aligns with the structure of F for the decider.
Okay.
Yeah. Yeah, I think I don't know if there is like a generically correct answer, right? Like if F has something that looks like CCS, maybe it makes sense to use that, or a proof system for that. Or if it has something that looks like Planck, then so on.
Makes sense. Makes
Yeah.
sense.
And I think I also have a comment on this. So, sorry, maybe there is something in chat, some comment. Yeah, there is a question in chat for you.
Oh, I can't see the chat. Hold on. Binary tree IVC like Paranova with using ProtoGalaxy. I have to hold 2 accumulators. Interesting. Yeah. I mean, as written in the paper, when you fold multiple accumulators, it doesn't really work with or the Lagrange version written in the paper does not work with folding multiple accumulators. Would it be better to go with the Lagrange version? I think for 2 accumulators, they might actually end up being almost the same. A sum check of 2 things is just going to have like 2 terms. And those 2 terms are maybe not exactly, but like almost just the Lagrange polynomials for a vanishing set of size 2. So I don't know that it makes a huge difference. It's probably, at least as written, easier to go with the sum check version, but it would end up probably being the same or very, very similar in overall performance characteristics to the Lagrange version.
I do have another question, which is in regards of the lookup arguments that we can plug in into here. Can you like at least give the intuition on how this will look like and will affect the folding equations? Like, do we just have like an extra term where we take into account all of the lookup related stuff, or like do we have another route to take?
So I think that, I mean, we don't talk about it in the paper, but it should be the case that the lookup argument from Protostar works with either very little or no modification in ProtoGalaxy. And the lookup argument from Protostar is pretty neat. It's log derivative based, but also each folding step does not incur costs proportional to the size of the table. You're able to like defer that all the way to the decider, which is very nice. In terms of like lookups generally, I think that would be the easiest one to use for sure, because you already have the stuff from Protostar, and hopefully it'd be just very similar to that. Something like which Lasso or something would be harder to integrate just because it's newer, and I don't know what the status of people folding Lasso is.
Well, my status is that it is possible to fold multi-round protocols, in particular GKR. But I'm not sure that you should fold Lasso. Maybe you should fold something like Logup. But it is sort of doable. Yeah.
Makes sense. Yeah.
Yeah, and I wanted to say that for decider, actually, I think whatever route you take, it is very likely that you would need to use higher degree gates, either higher degree gates or I would say that it's pretty unlikely that your arithmetization, if you optimize stuff correctly, of the decider coincides with what you can do inside of the protester. And so I think it's more more logical to just optimize for the folding and then have decider to emulate this in your arithmetization, in your chosen arithmetization, like for example Plonk.
Yeah, I think that sounds right. Yeah, definitely.
Okay, are there any other questions? Otherwise, we are on time already, and we should leave Liam after 1 hour and a half. So I will assume not, as I don't see anyone writing on the chat or asking anything. So Liam, thank you very much for being here today and for showing us the entire protocol and going through as many details as we have been able to ask. Yeah, it has been a pleasure. So hope to see you soon here, and as I said, very grateful for you coming.
Thank you. Thank you.
Cheers, everyone. Have a nice day.
Bye.